do our subscript hell, which means I want all of the kinetic energy before plus all of the potential energy before plus all of the spring energy before equals all of the kinetic energy after plus all the potential energy after plus all the spring energy after. I think I got that all set it out, but it's a lot going on there. It's a very simple concept, a lot of silly writing. So the 90% of this section, chapter in general, is doing before and after. When are things kept and when are things lost? And there's a word for it. There was a lot in the textbook. It really got wordy, and I just had to just put it right here. In the absence of non-conservative forces such as friction. So friction doesn't transfer heat. You can't, friction just makes heat. You can't like transfer that into something else. You can't like store the friction energy and use it later. That's not useful. That's why it's called non-conservative. And so it's just lost. When you have friction, the energy in the system is just it disappears from the system. It doesn't disappear from the universe. We can't create or destroy the energy, but it goes away from an object, and we're talking about where it goes. So we're basically going to go through the different pieces and figure out what kind of energies everything has at different places. So we're going to start the question at what kind of energy does it have at point A on the list. So at A, what kind of energy does this object, this block on a track, have? What types? Does it have spring energy? No, there's no springs in this question. Does it have potential energy? Yeah, it's up in the air. So it's above the ground and has the ability to go down, so it has potential energy. So I'm just going to write this. Potential energy. Is it moving? Yes, it's given an initial speed, so it has kinetic energy. So we just have to add them. That's it. We have kinetic energy, we have potential energy, add. So the potential energy is given by M, G, and H, and the kinetic energy is half of mv squared. So now we can just put the numbers that we know into this to get our total amount of energy in the system. This is going to be, depending on how big you write, we may have to flip over to the back of the page, which is empty, just in case you're wondering. But those of you that write small, you can probably get it on the bottom of the page, but that's what will happen. Just flip over. I have an infinite page here. I can just scroll up forever if I need to. Mass, 0.5. 0.5 times 9.81 times the height, in this case, we'll call 7. And then we're going to add with the other one, 0.5 times 0.5 times 3.0 squared. We'll get some numbers out of this. I haven't done this ahead of time, so I got to get my calculator out. 0.5 times 9.81 times 7, 34.335 plus 0.5 times 0.5, 3 squared. 2, oh, really? Yeah, it's not very fast. 2.25. Cool. Altogether, 36.585. And I'm keeping all those, and then at the over here I will go, energy is, it's going to round to 37, I think, joules of energy as like a final answer. So I'm going to shortcut us. V is equal to the square root of 2e over m. We did the algebra of that in another lesson. You should be able to get this algebra rearranged. And I can just put the numbers in this case. It's a very easy question. 2 times 36.585, all divided by 0.5 in a square root will get me the speed I want. Oops, let's hit those buttons. If I'm going 3 meters per second here, 12 meters per second here, up at C, I'm in the middle of those two, so I'm going to be between 12 and 3. I imagine 7 to 8, somewhere in that range. we're going to do the math on it, but like we're going to estimate it somewhere between 7 and 8, somewhere in that range. So let's do math. It's 4 meters up. So that's what I just had to check on the diagram there. Okay, so we just put these numbers in. We know these. We know EK will be, I want to look for, so I'm looking for speed, right? That's the goal. The question wanted speed. Yeah, speed at sea. So I want speed. So speed is in here, and so I have to solve for EK. So we're going to start by solving for EK before I put all the numbers in. It will make it less confusing if we start here, I think. So EK, whoops, wrong color. EK will be big E minus EP, right? This feels good so far. We have all the energy minus the height energy is going to be the speed energy. Now I'll throw in all the numbers, etc., that I know, which will be big E minus mgh. And now I can put in all the numbers that I want. Slide up so you guys can read. Some of you are looking around tall people's heads. Let's put this in here. Big E is the 36,585, the total energy of our system, minus the mass, 0.5 times 9.81, times the height in this case is now 4.0. So now we have this math to do. 8.585 minus 0.5 times 9.81 times 4. I get 16? 965. All right. Do we agree so far? Those of you that have tried. It feels right. So, what have I measured? 16.965. What have I measured? This is my kinetic energy, so I'm going to put the joules on top of it. So now I'm going to do the same equation I did above. I already know this one, so I'm not going to get too creative with it. The velocity is equal to 2 EK over m in the square root. So we know this is 2 times 16.965 divided by 0.5 as my mass, and I can get a speed here. So let's try this one. 16.965 times 2 divided by 0.5 square root. 823. Good, right where I expected it. That's too many numbers. Finished, the speed is, I guess it would be 8.2 meters per second in our case. Great. All right, so far this has been the easy steps. I've really kind of hopefully really over-explained these parts. And then we'll get into the last part is going to be where it gets slightly more detailed anyways. But it's still not going to be that much. So there's many ways to go about this. But we're going to try to go about this with energy. Because, anyways, let's just scroll back up the top and see if we can explain what's happening here. So let's go back up to the picture. I know it's a long scroll, and some of you are going to be on the back page by now, just depending on the size of your writing. We're now here, and we have a starting speed. So you can do this the old kinematics ways, right? You know you go from here to here, and you stop, and you know the coefficient of friction. You can do the force normal. You can do all those fun things to try to figure out what's going on. But so it was moving here and it's not moving here. So it had kinetic energy and now it doesn't. So what happened to that energy? Yeah, it's the friction energy. It was lost. So if we use lesson 1's words, work was done on the object, right? The work of friction was done on it. So we're going to try to use the work framework to describe how this happened. We can do it with just the forces and acceleration. We can do it that way, like last chapter, but we're going to try to organize it like work in this case. So let's try to organize it like work. So what we're going to do here is we're going to show, so we're going to say at C and D, the work done on the objects is what we're trying to look for. The work done will be the change in kinetic energy, right? It went from going fast to going nowhere. So all the kinetic energy disappeared. Where did it go? Into the work done on the object by the friction. So we're going to break down each of these things as we go. So this one, work, is going to be the force. What force was doing the work in this case? Friction work. So this is the force of friction and a displacement. And we know that the change in kinetic energy, I'm going to be sneaky, and I know that the kinetic energy is just this number right here. I've already done the math on it. I don't need to do it again. This is the kinetic energy at point C. I'm just going to use that number again. So I just need to go, that is just 16.965. I can be really cheaty, right? I already did that math. So I know the kinetic energy at that point. I can go back and do other stuff, but it's not important right now. Okay, so I know that's the joules. So all I need to do is now find the force of friction, because this is the variable I'm looking for. D is the goal of this. How far did I go? So it actually shortcutted a lot of the stuff. I don't need to find the acceleration, right? Normally I would, but I can skip that step if I know the work done. So this will actually make a little less math for us. So I'm just going to go slightly over to here and try to just solve for force of friction before I do the math on the other side, just because it'll get ugly in the algebra. Let's do force of friction. Formula given is mu Fn. That's a bad n. That's the n I'm looking for. What is providing our normal force in this case? Gravity is. So it's just the same as gravity. We have a horizontal surface. Nothing is pushing it up. Nothing is pushing it down. There's no slope. So we just can do, this is the same as mu times the force of gravity, right? And we know all of these things. All of these numbers are known to us. So we know the force of friction will be 0.40, because that's the mu given in the question. And we have 0.5 times 9.81. So we can just throw all those numbers in, and we get a newtons of force. I'm going to do the math on that now. 0.4 times 0.5 times 9.1. Oh, that is very little friction. But it's a pretty light box. 1.962 newtons of force. It's pretty little, but it's pretty light. It's pretty light. Okay. Yeah, not much stuff there. That's good there. Okay, great. Now we can go back over and solve for the displacement. The displacement will be the energy. I'll just write it twice here. Energy over the force of friction, which will be just 16.965 over 1.962. Oh, it is actually limiting me? Oh, I did get to the bottom of my thought I was infinite page. So it did stop me there eventually. So I got to the bottom of it. Oh, that should be it. Yeah. All right. This number, 16.965 divided by that, 8.64. I'll just leave it there. 8.6 will be the meters. I'll just round it right there because I'm out of space. Excellent. 8.6 meters is how long this thing slid to a stop. The diagram is not great to scale. The whole thing is 7 meters tall, and the CD chunk, they really shortened it. It's 8.6 meters. It took longer to stop than the whole thing was tall. But, you know, sometimes scale is shortened to fit things in the picture. Any questions so far?